Our next speaker is Remi Hendriks, and he will talk about measuring the efficiency of Anycast Routing.
Thank you. All right, hello everyone. Before I start my talk, I just want to mention that at the beginning of this conference, I was a little bit intimidated because it's a really close community, but everybody has been really welcoming, so I think that's really nice. So today, my talk is about this tooling I wrote. I'm a PhD student at the University of Twente, and I wrote it for research. But then as I started to develop this tool, we found out that there's also operational value for it. And after CCTLD operators started using it, we also repurposed it for operational use. And the goal of this talk is to make operators aware and to get some sort of engagement going and see if people are interested in this and how we can continue providing this for operators. So I don't think I will need to explain what Anycast is, but maybe just to give a quick recap, why do you Anycast? So one reason is to distribute load. So for instance, you want not all your DNS traffic to come at one location, so you want to distribute it amongst multiple points of presence. Another reason could be that you want low latency, so due to its geographically distributed nature, you can get closer to your clients and serve DNS closer to them. And another aspect, of course, is resiliency. So if an Anycast site goes offline, like in this example in the US, then the client, the resolver, can reach a different name server, for instance. And it's unsurprising that Anycast is widely used because it provides such great resiliency. In our census, we find more than 1,000 ASs deploy Anycast. And in nearly 2/3 of those, we detect active DNS services. And this covers the entire hierarchy of DNS. So you have the root letters that combined have almost 2,000 sites where they distribute their root services. You have authoritative name servers. So in this example, you see .fr for France, and you see that they have multiple Anycast deployments with different number of sites and announced by different ASs. You also have second-level name servers, so Google.com has Anycasted name servers. Resolvers, of course. This example is the public DNS for the European Union. And the problem is that Anycast is not performance aware because it relies on BGP, and often BGP routes clients based on the shortest path. The problem is that there are links like transits or remote peering links that are a single hop in BGP data, but they cover a large distance. So this might cause your clients to route to a different continent when they could be routing to an Anycast replica nearby. And I want to highlight two cases of suboptimal Anycast routing. The first one is the obvious one. Your client routes to a distant point of presence instead of one that's nearby. The second one is a little bit more complicated. It's a client that reaches a nearby point of presence. So if you were to look at your catchment, you would think this client is routing properly, but they're routing through a really long path or a really congested path. And in this example, you have a boomerang route where they travel through the US. So, as I mentioned, Anycast routing can be suboptimal. Clients can reach distant POPs, and this can lead to high latencies, long paths. They can traverse congested links. This can lead to packet loss, and it's not optimal. You can also find that certain POPs attract more traffic than you would like. If they're, for example, connected with a really well-connected IXP, then they can attract more traffic, and the load distribution is not optimal. And to combat this, you need performance metrics. You need to know which resolvers go to which of my name servers, or which clients go to which of my resolver, and how do I plan my infrastructure to handle this. But you can also use these metrics to perform traffic engineering, so to divert people to different places. But how can you get these metrics? So the obvious one is you just monitor the DNS traffic that you're already receiving. This data is already available. There's no burden on this. And you have high coverage because you see the data from all your clients. The downside is that you cannot measure proactively. So if a client routes suboptimally or they can't reach you, then you only find out after it has happened. Another problem with the DNS especially is that you might not get the latencies from this traffic because regular DNS over UDP, it's impossible to infer the latency. There are tricks to get this from passive data, but they're often limited. And another limitation, because you cannot measure proactively, you cannot measure a new deployment or a new expansion before putting it into production. The second is related to Giovanni's talk today about RIPE Atlas, so the route viz. And this is also really nice, so you can measure from the outside how does the internet connect to your Anycast deployment. But I do want to say that there are some downsides to this. So these platforms often have rate limiting, there's credit costs. He also showed that there are some RIPE Atlas probes that just have timeouts. And especially if you want to limit this to anchors, then the coverage is really limited. Then there's this third technique, which I will be talking about, that the tooling uses, and that's by probing responsive hosts on the internet with an Anycast source IP. So to give some background, this is based on a technique that Verfploeter uses from Wouter, who's also here. And what Verfploeter does is it sends pings with an Anycast source address to ping responsive host, and then the ping responsive host sends back a reply, and then you can see where the ping reply ends up, and you know the catchment of that host. So in this example, the light blue dots are our Anycast deployment, and you can see that this client in Oklahoma receives a ping from us, and then we can see where the ping reply comes back. So in this case, this client routes to Salt Lake City. The advantage of this approach is that there are a bunch of ping responsive hosts, and you can cover more than 70,000 autonomous systems. And you can also measure proactively and on demand. So for instance, you see a routing event in BGP, then you can spawn a measurement and see how this affects your deployment. Or one of your sites goes down, what happens to the traffic distribution. You can also use this to measure experimental prefixes or new deployments you want to try out. But the disadvantage is that this only measures the catchment but not latencies. And it's not always clear what the optimal site is. So is this client in Oklahoma routing to Salt Lake City, is this the best decision, or would it better be to go to Nashville or maybe to Phoenix? You don't know. So I will not go into detail about the implementation due to time. But what's important is that this is designed as a Swiss knife, so we support as many measurements as possible. The tool is really low resource usage. It's a small binary you can deploy. It's also containerized if you would like to deploy it with Docker. And it supports TCP and UDP as well. So if you have the concern that ping traffic is not representative for the UDP traffic that you see with DNS, then you can also do these measurements with UDP. And of course, it supports IPv6. So the first the measurement type we implement is our Anycast RTTs, so you can measure the latencies that clients experience towards your Anycast deployment. And what it does, it first sends a regular discovery probe to measure the catchment, and then it sends a second probe from the catching point of presence, and then you have a symmetric case where the sender is equal to the receiver, and you can measure the latency just like regular ping. I do want to mention that we validated this method thanks to SIDN, who deploys this in practice, and we were able to see that the latencies we measure match the ones they got from their passive analysis. And we also saw that there is a large correlation between latencies with TCP and ping. So a second measurement type we implement is to infer what the optimal route could be. And how this works is you send pings from all your Anycast sites to the target network, and you measure the RTTs to for each point of presence using its unicast address. So then in this example, you would know the latency towards each of these 4 points of presence. And then if you pick the one with the lowest latency, you know what the optimal site would be for this client. And what's nice is that you can, first of all, you can see which site it should route to if you were to optimize for latency, but you can also quantify the improvement. So if the client is not routing to the optimal site, but the improvement is only a few milliseconds, then it's probably not worth the traffic engineering. So now I will go over some results to showcase the tooling. It's mostly to show its usefulness and to give you some inspiration on what kind of use cases it can have for you. I think Giovanni also showed a lot of interesting insights, and you can derive similar statistics from this approach. I do want to mention that if you Anycast your deployment using Vultr, then these results will be representative for you. So this is a map of the 4 million target networks that we scan and how they connect to our testbed. And they're colored by the latency, and the size of the circles indicates the number of networks there. And what we see is that in Europe and the US, you see low latencies, which is expected because there are a lot of points of presence there. But in China, we see a really large RTT, which is understandable because we don't deploy there. But also if you zoom in on southern France, you see higher latencies. So this plot shows the optimal latency, so the lowest unicast latency for each target network. And this kind of gives you an insight as to how the performance could look like if you were to somehow optimally route all clients. And in this example, you can see that China is still pretty horribly. So this suggests that Vultr lacks points of presence in China and that the deployment would benefit from this. But we also see that the ones in southern France turned green. So this means that those networks are routing suboptimally, but they could be routing to a good POP and experience low latency. So the takeaways are, with this latency approach, you can see who routes well and who routes bad. And with the optimal latencies, you can see who could route or who could achieve low latencies if you were to perform traffic engineering. And the places where there's no good RTT, even in the optimal case, those are indicative of areas where you want to expand your infrastructure. So to give another insight, I'm going to zoom in a little bit on a case study. So we built a dashboard around this tool that takes the data. In this case, we select an area in China, and we can see that it has really high latency, and that's because they're routing to Frankfurt. But we see that the optimal latency is also really high. It's 110 median RTT. And that's, that's for the best case where they route to Tokyo, but that's still bad. So this is, you want to expand your infrastructure there. And you can also do this by ASN. So you can see which ASN routes where and where should they route and what are the latencies they observe. Another case study, so on the left, so for some reason, a lot of networks route to the Mexico instance of Vultr. I don't know why, but like 20% of the internet goes there. So on the left, you see the networks that all route to Mexico. So you see a lot of in the US and also Europe, and especially the ones in Europe have really high latency. And on the right, you see the ones that should be routing to Mexico based on the optimal RTTs. And well, this shows you that you should be implementing traffic engineering to steer away those European networks to European POPs. But the ones in the South US, for example, maybe there is a better point of presence for them, but they're also fine to go to Mexico because they have low latency. Maybe Trump would disagree, but... So this plot requires some explanation. So on the y-axis, we have the measured latencies, and on the x-axis, we have the distance between the client and the catching POP. So that's based on the catchment. And on the left, we see that most networks are on the bottom left, and these are networks that route to a nearby Anycast POP and they experience low latency. But we see that there are also some that, despite going through a nearby point of presence, they still experience latencies up to 100 milliseconds. We even see some outliers for 200, and these are these boomerang routes I discussed previously. And on the far right, we see networks that route to really distant points of presence, and we see that this is also reflected in the latencies. There are a few lines between the speed of light line I plotted, and these are geolocation mistakes of the database we used. So the takeaways are that the catchments are pretty good for inferring if people go to the right pop, but it can be misleading because of the boomerang case, but also there might be congested links, and you want to know these cases. So we argue that RTT is a better indicator, both to detect congested and long paths. So next, we did the same, except we correlated it with the hop count. We do see that there is some correlation, but it's quite weak. So it seems that the number of hops that clients traverse does not really have that much of an impact on the latency. And this does make sense because a lot of transits and remote peering links use tunneling, and then it's only a single hop in TTL, but it would be a large increase in latency. And what this shows is that TTL is a poor indicator of performance, and if you optimize your DNS deployment based on TTLs, which you might obtain from passive data, then you will not improve the performance for your clients. And yeah, we argue that the tooling gives better metrics with latencies. So there's also other techniques we implemented. One of such is Anycast traceroute. And what this does is you can send a traceroute using an Anycast source IP, and well, you see all sorts of weird stuff because each individual hop might respond to a different, might go back to a different point of presence. Especially when you have like a client in Asia that routes to a POP in Europe, and you traceroute to it with an Anycast source address, and you see like the hops go everywhere. And this is really useful because first of all, you can map more networks, because some networks are not ping responsive, but they might respond with time exceeded. And it also helps you to troubleshoot suboptimal paths. So you can have some sort of indication as to which AS is sending your traffic to a different continent. Another implementation we have is measuring Anycast site flipping. And what this is that you might have some networks or resolvers that have subsequent queries to send to your DNS servers, and these subsequent packets will reach different POPs, which can be problematic, especially if you do DNS over TCP. So to conclude, we built MAnycastR. It's open source, it's public, anyone can use it, and we originally designed this for research purposes, but we found out that it has a lot of operational value. So you can do catchment mappings, latency mappings. You can use it to perform traffic engineering, to strategize how your deployment should evolve. And it also helps you to find out where clients should go to using the optimal routing inference. And we think that the tooling can also be helpful in attack mitigation. So if you, for example, withdraw a certain site, like how does the traffic redistribute? That's something that we also think could be useful. So for the Q&A, we also have some questions for you. So what do you operators care about? Do you care, does latency even matter for a DNS operator? Or do you care about short paths? Maybe GDPR compliance that you want to stay within, like the jurisdiction is important. Is load distribution more important, or just the resilience angle of Anycast? And would this tooling be useful for you in realizing these goals, and what kind of requirements would you have for using it? So we're open to feedback, and we're also interested in active collaboration. So if you want to use it, please share data. You don't need to, but we would really appreciate it. And we're also looking into other topics like measuring Anycast routing in developing regions. You can contact me or you can approach me. I'll be here for the right meeting as well. And I also have a demo for people that are interested. Thank you.
Questions for Remi?
Yeah, Ray Bellis, IC, still running Verfploeter. Thanks for that, very interesting. Some perspective on this for us as a route operator. We're kind of lucky that we actually don't have to go looking for new sites, so we don't actually do much by way of optimization. Generally, people come to route server operators to say, can we have one? For me, my consideration usually is, will the internet be improved in your vicinity by adding a node? So that tends to mean we go for IXP sites rather than transit sites. Yeah, but so basically multiple ASs in the region can benefit. We do look at latency subsequently, but not for performance reasons as such, but simply because latency is a very good first order approximation or proxy measurement for geographical closeness. We do focus very closely on how tight the catchment areas are around our nodes and make sure that we're not sort of leaking to large numbers of nodes in other continents, for example. So that's really for us the main consideration. In terms of resilience, it's not so much about, it's not, certainly not about load distribution. We don't worry about load distribution at all. When we look at resilience, it's more about resilience against things like DDoS. I'm very focused on making sure that if a particular node is DDoSed, that the geographical effects are very, very constrained. So it's not really about just saying, well, I've got 10 servers, one goes down. It's not so much about that. It's just make sure that the rest of the internet can run if that particular one goes out. So it's not really about paths, but very much about just keep the traffic locally to where it needs to be.
Okay, great, thank you.
Hi, Dave Knight, Nominet. First off, I think this is fantastic. I really want to go and play with that tool. Also, I'm very glad that you're having a nice time at OARC. Does RTT matter for DNS Anycast? Yes, as soon as you're selling it, it matters a lot. So do you optimize for short paths? Sure, because we care about low RTT. On load distribution, I'd make a distinction which you haven't, which is there's both global scope and local scope. Anycast, you're speaking about things in global scope and BGP. Where we think about load distribution, I think about it more in terms of locally, within a rack, we're anycasting between stacks of servers. Obviously, it'd be far more convenient to just have one data center, one place in the world. We'd still be using Anycast to distribute the load amongst the servers, just not geographically. I think that's everything I had to say in feedback. But I really look forward to playing with those tools. Thank you.
Yeah, great, thank you.
Hi, Wouter de Vries from Cloudflare. We also care about RTT a lot because we sell DNS to people.
Right.
They care about RTT, so we do also by extension. We also care a little bit about load distribution, I would say, because sometimes we see the instance where we have a very small POP, and then because of the wild variety of routing policies out there, sometimes it may be the case that a very large site, such as an AWS DC, decides to route all their traffic, all their DNS queries somehow to one of our very small points of presence. So there we also care about this. We actually use also this a tool very similar to yours. I was also wondering about for attack mitigation. I had once had the idea to, if you know where an IP address is supposed to show up, and someone spoofs an IP, they can't spoof the routing. So if it shows up in a location that's not within its catchment, then you could say, okay, well, we're not going to answer this query, for example, or we're not going to respond to it, and then kind of mitigate like spoofing attacks. That's I don't know if you've tried that, or I think you work with .nl maybe.
Right. Yeah, so this is something we're thinking about. One of the features I want to implement is reactive measurements, and then if you see an off-catchment address that is likely spoofed, then you can spawn up like a reactive measurement to verify that it really is off-catchment. Because there might be, you don't want any false positives and block legitimate traffic.
Yeah, that's a concern. Thanks.
Thank you.
Thank you, Remi.
Thanks.